Good morning, ladies and gentlemen. Today we are going to start a new topic of magnetism. But before we talk about magnetism, of course, we have to talk about what's a magnet. Well, we already know that every magnet has a north pole and a south pole. And similar to electrostatics, we know that opposite poles will attract and like poles will repel. But they're not the same as electrostatics. In fact, the biggest difference is that with electrostatics, you can have a positive charge or a negative charge based on whether an object is either missing electrons or has too many electrons. But with a magnet, if you took a bar magnet and you broke it in half, you simply end up with two new bar magnets. In other words, every single magnet has to be a dipole. It has to have both the north and the south pole. Now, part of the reason for that is because of what we call magnetic domains within the magnet itself. You see, you're going to learn later on that moving charges create a magnetic field. So every object is composed of billions of protons, neutrons, electrons, and those electrons that are moving around generate a magnetic field. But most of the time when you talk about electron spin, they have opposing spins, so all those magnetic fields cancel each other out. But few specific types of materials have the electrons spinning in the same way. So therefore, they generate a magnetic field, a stronger magnetic field together. And that's what we call a magnetic domain. Okay? Magnetic domain means that literally within the magnet itself, there's billions of little magnets pointing in the same direction. And those magnetic domains are easily influenced by other magnetic fields, similar to this video over here. So if you were to imagine here, this person just mounted a lot of magnets, but if this were just a block of some sort, okay, you can see that within, if you were to look at each individual magnetic domain, each individual atom of the block itself, you can see that these magnetic domains are willing to be moved around whenever you place another magnetic field near. And the professor right now is just moving a bar magnet near all these other magnets. In fact, if you eventually align them all in the same direction here, you can see they're all pointing a certain way. And over here would be north, and over at the other end would be south. Sometimes they don't all line up and they will actually cancel each other out, which is why certain magnets are stronger than others. But when they're all perfectly lined up, it creates a stronger magnetic field in a certain direction. So in general, if you took a regular piece of iron, which is able to be magnetized, but if it's unmagnetized, it simply means that its magnetic domains are pointing in random directions. They all cancel each other out. But if you expose that iron to a magnetic field, those magnetic domains will slowly start to align until it becomes much stronger alignment, and they are all pointing in the same direction. But because these magnetic domains move around all the time, that's why magnets do lose their strength if they're dropped or heated. If you were to simply bang a magnet on the table, it would lose its properties. Okay? Simply because those domains jump and they realign themselves. So the magnetic domains would realign themselves randomly. And it's this fact that simply proves that when people say that the Earth is a giant magnet, we already know that the Earth has a magnetic field, But why does it have a magnetic field? And a lot of people incorrectly assume that's because of its solid iron core. But this is impossible. And this video
Questions
explains
whose answers
why.
turn out to be a little bit more complicated than you would think at first glance. Let's start with a common misconception you might have about the Earth's magnetic field if you had teachers like I had. The Earth's magnetic field originates from the solid iron core of the Earth. Sorry teachers, it's not that easy. The solid iron core of the Earth is about 5500 Kelvin hot, which is about the temperature of the Sun's surface and way beyond the Curie temperature of iron. Beyond the Curie temperature, iron loses its ferromagnetism completely due to entropic-driven disorientation of the individual magnetic moments in the solid.
So you can see that the Earth is actually way too hot for iron to hold its magnetic properties. So magnetic domains will end up realigning.
So the real answer turns out to be a little bit more complicated. The inner core is surrounded by a liquid outer core, which is also rich in iron and nickel. Because of the high temperatures, the metals are partially ionized, so the liquid inner core is electrically charged. The temperature difference between the core and the crust leads to convection in the outer core, and the Coriolis effect caused by the Earth's rotation organizes this flow into rolls aligned with the rotational axis of our planet. Now, since we know that charges in motion create magnetic fields, we have already found our solution. But I don't want you to get the wrong impression.
Okay, so that explains why, well, the Earth has a magnetic field, simply because of those convection currents with along the Coriolis effect moving those charges. But those convection currents do move extremely slowly. I mean, you've taken Earth science already. But because they move so slowly, that's why the Earth generates such a weak magnetic field. Now, to represent that magnetic field, okay, we're going to use magnetic field lines, just like we've used for electric field lines or gravitational field lines. And the same rules do apply. You know, the lines can never cross each other, and that the density of the lines indicate the strength of the magnetic field, which again is represented by the letter B. But the most important thing to remember is that magnetic field lines go out of north and into south. So if you take a look at our bar magnet at the bottom over here, you could draw literally a magnetic field that goes out of north and into south. Okay. In fact, if you were to take a compass, okay, now a compass itself is a magnet also. So if you were to take a compass and place it along this magnetic field anywhere along, you would see that it will point in a certain direction, because the compass, the north side of the compass gets attracted to the south pole of the magnet. With a horseshoe magnet, well, we can see more clearly over here, this person does an excellent demonstration of what the magnetic field line looks like. You can see that his three-dimensional model over here shows the magnetic field lines, I'll pause it for a moment, are going out of north and into south. Okay, and they'll cross over here as well. The fact that people going around and around, and the magnetic field lines will never ever cross. Later on, he uses a regular bar magnet, and you can see with the regular bar magnet with the north and south pole that the magnetic field lines are going out of north and into south in a three-dimensional model. Okay. Okay, so over here, I just want you guys just to understand that if you were to throw iron filings near a magnet as well, those iron filings would instantly magnetize and draw out the shape of the magnetic field lines. Ultimately, it would go out of north and into south, and this applet just does a wonderful job of demonstrating that. Now, remember how I said that compasses, the north pole of the compass is attracted to the south pole of a magnet. Well, I just want you to understand that if you were to really think about that, when I say that there is a magnetic field around the Earth, okay, the north pole is actually a magnetic south pole, which is why if you put a compass along here, the north pole of the compass will point geographically north, but that's because the north pole is really a magnetic south pole. And yet scientists have already shown that actually every 100 million years or so, the magnetic field of the Earth does switch. And we've shown that with different geographic digs that we've done, geological digs that we've done, but it's just a fascinating idea nonetheless. Okay. So even if you have two bar magnets near each other, we can always say that they go out north and into south. It's easy enough. And like electrostatic fields, they're going to repel away from each other if they're the same pole. And we do know that magnets can share the magnetism with other objects, mostly iron, cobalt, and nickel. And the fact is, when we draw these magnetic field lines, it's because these magnetic field lines are able to permeate through the iron and realign its magnetic domains so that way they're all pointing a certain direction. But note, okay, and this is important, when I draw the magnetic field lines, I do say they go out of north and into south. But inside, you can see overall it actually completes the loop. Inside, it goes from south to north, okay? Because inside the magnetic domains are pointing which way north is. So overall, you do have a complete loop. It does go from north to south outside, but inside it'll go from south to north. Now, things that are not easily magnetized still technically can be magnetized. Iron, cobalt, nickel are just the easiest ones. And just to prove that to you is this great video over here. This is they put a giant magnet, and they actually magnetize liquid or even a frog. And this frog is floating inside a magnetic field because it's been magnetized. We have another liquid over here. And later on, they have a tomato that they magnetize and it's floating around in that magnetic field, or a cricket. So the fact is, we all have magnetic domains within ourselves. It's just that most of the time it's so weak that it can't be magnetized. But if it's exposed to a strong enough magnetic field, you can see ultimately that it does get affected. So we do just a couple practice questions here. Which diagram correctly shows a magnetic field configuration? The answer, of course, is not 1, because magnetic field lines go out of north and into south, and that's why it can't be 2 either. It can't be 4, because magnetic field lines can never cross each other when you're drawing it, which is why the answer is choice 3. And if we take a look at the next problem, which diagram correctly shows the orientation of a compass? Well, remember, a compass it points geographically north, but still a magnet itself. So in the end, the south pole of the compass is going to point towards the north pole of the magnet, which is why the answer, again, in this case, is choice 4.